All right, good afternoon, everyone. I'm Daniel Mountjoy. I'm going to be the moderator for this session. I work with a number of these folks, and some I haven't worked yet with. I work with Sustainable Conservation, and we are working on this whole groundwater issue in terms of especially focusing on the farmland portion. And we've got a great panel here, starting with Graham, who's going to outline some of the recharge floodplain potential. And then we've got, after Graham, we're going to switch over to Efron Goharian, who's going to talk more about the headwaters and waters coming down out of the whole drainage system. And then Helen Dalkey, who's one of my colleagues that I'm working on-farm recharge, talking about winter irrigation. And then finally, Andy Fisher talking about issues of incentives and net metering concepts for how do we motivate people to do more of this work and give them credit for the work that Graham said, have been doing historically. So with that, we're going to start with Graham.
Okay, you get to hear me again here. I'm not sure where to stand. Maybe I stand over here. I'm going to talk about floodplain recharge, but first I want to sort of set the table in terms of the bigger recharge picture in the context of what's going on in UC Water. I'm going to show you a well hydrograph very quickly now from Yolo County, shown here. And this well hydrograph in particular, look at the last about 10 years. This is what we're seeing a lot of in Yolo County. This is an irrigated area. And what's going on here, we think, is less groundwater recharge because of more efficient irrigation and less use of surface water. We're seeing this broadly across the county. Just to make the point that a key aspect in groundwater is not just using less water, but in some cases irrigating less efficiently when you have surface water to recharge the groundwater. So I'll leave that, and we can come back to that, but it kind of sets the stage for what I want to say in terms of water storage in California. We've got 140 reservoirs that store 42 million acre feet. In Central Valley, there's a room for another 140 million acre feet in the groundwater. That's the depletion of the groundwater over time. So that's obviously our biggest vacant reservoir right there. And so the key is how to make better use of it. To what extent can you? Now, where's the water come from? Pre-development Central Valley recharge is about 2.6 million acre feet. Post-development, 5.6. So farming resulted in, it varies from a doubling to a tripling of recharge. So in most of the Central Valley, most of the recharge is from farms, or has been. Now, where's the other source of water? It's the rivers. Pre-development Central Valley floor river recharge was minus 1.2. That means the groundwater was discharging to the rivers. Post-development Central Valley floor river recharge was about 1 million acre feet, a gain of 2.2 million acre feet. So between the river recharge and irrigation, we have seen huge gains in recharge. So the capacity of the system to take in more water is there. It's just that everything that's happened up until now has been unintentional. So part of the question is, well, how do we make it more managed and intentional and perhaps more effective? And therein lies the joint consideration of farms and the rivers. Those are the two main levers we think we have for managing the system differently. On the Cosumnes River, the Cosumnes is a river basin that drains the Sierra Nevada. It's not shown on a map right at the moment. That is south of Sacramento, essentially due east of here. And a levee was taken out to let the floodplain flood. And after waiting to get by 3 years of drought to actually see the river flood, we collected data and we've been measuring floodplain recharge. The upshot of it is we get about 2 feet of recharge per event. And the system floods more frequently now because the levee's been taken out. So we have, for this little 280 acre or 144 acre plot, we've got on the order of almost 1,000 acre feet per year that can get into this. So that's Just for comparison, a typical farm recharge might be more like a half to 1 foot of water per year. So this is 2 to 4 times what you would get from farm recharge. And one idea is to open up our floodplains in more areas where we can, obviously where they're not urbanized, to let that recharge benefit the groundwater system. And the theme here is very much, it's not going to be like 5 big projects that revolutionizes how we deal with groundwater. It's going to be 1,000 projects. And to have 1,000 projects, you need incentives, which is going to come to Andy Fisher's talk at the end of this. So I'm going to leave it at that and turn it over to Irfan for the next speaker.
And we are going to go straight through, and then we'll have questions afterwards.
So, Graham talked about we want to do the recharge, but where the water comes from. And in terms of sustainable groundwater management that we talked about, SIGMA, one of the most important part or role of the surface water is to check and estimate how much available water we have for recharge, and mainly from surface water and stormwater, water conservation, recycled water, desalination, and water transfer. So what we did, we came up with here is the map of the Cosumnes and American River. And so we wanted to make sure and estimate how much water we have from the system upstream of the American River, and also including Folsom Reservoir, and also exclude that by looking at the full natural flow from American River. So you saw this picture before. When we want to check, okay, do we have enough water, first of all? And if yes, where do we want to put that? How do we want to do the recharge? Do we have enough capacity in the groundwater or not? I mean, that's extra water that we can't really recharge that to the groundwater. So for that purpose, we need to do integrated modeling of different modules and sections. So let's more talk about the American River and the study we did. Basically, if you want to have an understanding about surface water condition in American River and specifically in Sacramento Basin, there is a SVI index which categorizes the water year type from wet to critical. So 5 different classes. And by looking to the historical condition, you can see about we have 32% of years from 1922 to 2002, 32% of times we had the wet year. And also the critical and dry is 37. So equal dry years and also wet years. But if you look at the full natural flow below at American River, you will see a slight increase and a slight increased trend in American River flow. However, that's the annual one if you look at the unimpaired flow. But if you look at specifically for month May, if you look at the May, we will see a decrease. And then if you look at March, we'll see still increase. So first thing which comes to our mind is that, okay, this is the proof of concept we had early snow melt up in Sierra Nevada. And also we should more carefully investigate, okay, how these changes can affect in downstream. So I look at more carefully to the condition over almost 80 years from 92 to 2002 again, and divided the years to dry and wet condition. And you can see for wet condition we have increase, and for dry condition we have constant situation. And the thing is that, so if you look at the magnitude of the high flows is increasing, but the dry, we almost had dry condition, the same dry condition. However, the most important thing is that in comparing to the wet years, we have longer droughts. So the period of droughts are longer, the magnitude is the same. However, for high flow, we have increase in magnitude. So, which brings this question: how do you want to like deal with this system? Do you want to like still? We cannot like keep this much water, these like high peak flows, and in wet years in surface reservoir, and like keep them for like 5 years, 6 years drought after 10 years, or like after we had that magnitude. So we came up, okay, groundwater is a great place. We have almost similar capacity in Central Valley. So we look at, okay, we want to do the recharge, but what's still the role of reservoir in our specific case where we have the Folsom Reservoir? So if you look at the full natural flow and compare it with the releases from Folsom, you will see that the reservoir has kind of like make it relaxed. We don't see like the high peaks and low peaks and seasonal changes in releases from Folsom, which gives us this opportunity to kind of like capture these high peaks and use them later for recharge. So if we kind of like summarize, if I wanted to mention how much available water we have from Folsom in different conditions, full natural flow, which it shows the maximum hydrological capacity of water we can capture for groundwater recharge, and also looking at the historical releases from Folsom. And available water is, I take out the minimum flow requirements from the releases, and also consider all the infrastructures that we have, capacity of infrastructure to transfer water from Folsom, downstream of Folsom, to the point that we want to do the recharge. And you can see we kind of like have about 600,000 acre feet per year to do the recharge in different conditions. Extended winter, which comes from November to March, and also winter recharge from December to February. So we kind of like slightly have more chance to use the benefit from reservoirs to increase the available water for recharge. And again, I didn't include the water rights for sure. This is not something you can really do, but this is shows if we have this much water, how do you want to use it? And the other thing is that we should check the lowlands or the downstream to make sure we have enough space to put this much water in ground. And when we are talking about 600,000 acre feet, if again we classify the values in terms of the critical to wet years for from historical releases from Folsom and also full natural flow, we're talking about 20 to 30% of whole water during the critical, and also about like 10 to 15% of total water we have during the wet seasons. So it's just 10% maximum water we can transfer to downstream or to the point that we want to do recharge. It's just 10% of the full natural flow during the wet season. That's it.
Right. Just advance it once more, if you would.
Which is a perfect transition into the next topic. I will talk about winter irrigation. I personally don't actually call it winter irrigation, but I actually more adopted the word ag recharge, which was proposed by Thomas Harder at some point. And under ag recharge, what we understand is as more or less a managed aquifer recharge approach. But instead of using designated infiltration basins, the idea that we are pursuing is that we are using agricultural lands, fields in production in the Central Valley, for example, or as spreading grounds for water in the winter. And that is research that has been started as early actually as in 2010. Phil Bouchon, who's in the room, was involved in a project conducted at Terra Nova Ranch near Helm in California. And they actually really tested that principle on the farm, on the ground, by spreading or diverting flows from the Kings River and spreading it onto various fields that were planted with grapes, alfalfa, pistachio. And since then, we have really taken this initial study to heart and have expanded it to really address several questions, which I have here sort of arranged in this wheel of questions. So in order to get water back into the ground that is not entering the groundwater from inefficient irrigation, but rather thinking about it as like an intentional artificial recharge operation in the winter, we really need to know where are suitable locations where soils have the capacity to convey a lot of water in a short time. And that is in particularly needed because most of the rainfall that California gets comes in very short rainfall events, so-called atmospheric rivers in some cases. And they only last a couple hours or days, so your time window of having, when you have a lot of water available, is very short. And in order to compensate, to really make use of that volume, we need large spreading grounds and infiltration basins that many water districts have throughout the Central Valley. They just simply don't have the capacity to take all of that water in. So the idea is really to use agricultural fields that are typically really well connected to conveyance systems such as irrigation canals and use them as spreading grounds. And some of you might know that the land use in California Central Valley is changing quite a bit, or has been changing over the last 50 years. So instead of planting a lot of annual crops, we're moving more and more to perennial crops, like it's tree and fruit and nut tree crops. And applying water on perennial crops is really a question that needs to be investigated first, because that is the farmer's investigation, and we don't want to risk or cause any cost to the farmer if they're offering their fields as spreading grounds for groundwater recharge. And if we are growing crops on fields, then the next question, of course, is water quality. What happens to all that nitrate that is applied in the summer during the growing season? Aren't we just like washing that nitrate down into the subsurface? So those are all ongoing questions, but to give you a little bit an outlook, there's more detail coming tomorrow. I'm giving 2 presentations tomorrow at 2:25 and 4:50 in the afternoon. We are currently conducting a lot of on-the-ground experiments throughout the Central Valley and in the Scott Valley in Northern California. And we are testing on-farm recharge on different cropping systems, including alfalfa, almonds, walnuts, and pistachio. And for the alfalfa, we have already completed 2 years of data collection. And I can tell you that this is biomass data collected from our site up in the Scott Valley, for example. If we, or here in this case, we have applied up to 29 feet of water on an alfalfa field. So that is almost 10 meters of water column. And we only saw a slight decrease in the biomass yield in the second cutting that equaled more or less half a ton per acre after you've applied 29 feet. So that looks pretty promising. And other recharge studies are ongoing on almond fields. And we don't have the yield data yet to really tell whether or not the trees can tolerate it. But some other aspect that we're looking into is also looking at surface water availability. And in contrast to Erfan's study, who's looking mainly at the American River, we have looked at USGS daily observed stream flow data at different gauges, 93 gauges throughout the Central Valley, and have really looked only at the high magnitude flows. So when you actually apply for a water permit for your surface water in the state of California, the availability is calculated on average mean annual flows. And as Erfan was pointing out, we do have wet years in California, so when the annual flow is much, much higher, in some cases 150% of the average flows. And we really think that additional water that could go into the ground comes from these high magnitude flows. And to show you some of the estimates that we have calculated, if we look at only flows above the 90th percentile, the Sacramento River has, in average conditions, when we do have flows occurring above the 90th percentile, we see 7 million acre-feet of water going out into the delta, into the ocean. California has an average overdraft of 1.5 to 2 million acre-feet per year. So you might get an idea if we just take like a third of that 7 million acre-feet and find a way of getting it down south, we might actually be able to address some of that groundwater overdraft in some of the regions in California. And I also wanted to show you this little decision support tool here, which has been developed by Toby O'Gene at UC Davis, a soil specialist. Farmers need tools to help them make decisions. In this case, Toby has taken all the Sergo soil survey data that we have available in California and has come up with a ranking system of these soil types in terms of suitability for ag recharge. So if you see green areas, that means those soil types are very suitable to convey a lot of water in a fairly short time if applied in the winter. And so this tool is online, and you can Google it, use it on your phone when you're out in the field. Thanks. I'm handing it over to Andy.
I'll stand over here too.
Yes.
So I'm going to describe a new program that is being launched on October 1st of this year to provide an incentive for managed aquifer recharge projects which primarily use stormwater as their water supply. And I'll just point out before we get going that much of the work I'll present is from data and analyses compiled by the research group that's responsible for this and related projects. So this area that we're going to look at here is central coastal California. It's about 50 miles south of where we are right now. In the southern central part of Santa Cruz County and Monterey Bay is this groundwater basin called the Pajaro Valley Basin. If this were a county in California, it would be the smallest by far. It's smaller than the San Francisco, but it would be number 5 in the dollar value of ag production. It's an area of very high value crops, cane and strawberries and a variety of vegetables and organic crops. We have one site currently operating in the central back part of the basin. It's shown here. The area in tan is drainage of about 170 acres off of an active ranch where a variety of crops are grown. And water is being redirected off of the landscape during storms, flows through a small settling basin, and then comes along a ditch, through a culvert, and into a 4-acre infiltration basin. I'll describe a little more about this tomorrow afternoon during the session, but even during the drought in water year 15, when we had that big rain event in December, there was so much rain in just a couple of days that we hit the project goal of 100 acre-feet, really in about 4 days. So this really speaks to what Helen was talking about with the intensity of the storms and what Irfan was talking about as well, that if we have mechanisms to collect water during brief periods, we can accomplish a lot of benefit that would not occur if these systems weren't in place. Now the challenge is that these systems take land, which then comes out of production, and that's a cost. They also require operation and maintenance once they're put in. And the maintenance might be minor. It might just be scraping the sediment off once a year, but that's a cost. So how do we offset either the landowners or the growers or the ratepayers, whoever they may be, for allowing projects like this to occur on their landscape? And there's a model for this. It's a model that has been around in California for a little while. And this is from the PG&E website, and it describes this program of net energy metering. And the way the system works was that if you have solar panels on your house, and you generate power that you use, and you have power left over, you can put that power on the grid, and your water meter, your power meter actually runs backwards. Now, Much of California groundwater is not currently metered, but that's changing. Over the next 20 years, as Signal becomes implemented, there will be more places in the state that are metered. In addition, in most places in California, pumpers of water don't pay a fee for that privilege. They pay for the well, they pay for the pump, they pay for the pipe, they pay for the electricity, but they don't pay for water directly. Well, that also may be changing. In the Pajaro Valley, most pumpers pay an augmentation fee for the privilege of pumping their groundwater. It's about $190 an acre foot in most of the basin, and it's close to $300 an acre foot in part of the basin for a variety of reasons. So there's a fee people pay in order to pump their groundwater. What if they had a way to get some of those fees back? And that's the concept behind what we describe as recharge net metering. So here's an example of how it might work. Imagine you've got a ranch, it's about 75 acres, they're growing berries, they need 2.5 feet of water per year to grow their crop, so their net pumping might be about 190 acre feet per year. If they're not participating, they will pay for that water. I'll talk about the cost in a moment. But now imagine that they're collecting stormwater runoff from an area the size of the project I just showed you, about 200 acre feet. So with reasonable estimates of the runoff coefficient, they might generate something that's about 120 acre feet of runoff. We subtract the incidental infiltration that would have occurred anyway, even if there were no project, and apply that as an offset. So their net pumping is 60 acre feet. Imagine that they're capturing runoff from a larger area, 400 or 600 acres of runoff. Well, in that case, they actually have negative net pumpage because there's more water going into the ground than they're actually producing to grow their crops. And in terms of how this would be applied, if you imagine a 50% fee reduction on the augmentation fees for the water beyond the incidental infiltration, that is the infiltration benefit that's being provided, the baseline fee for this grower is about $36,000 per year. That's what they're paying for their water. Okay? Now, if they institute a program that allows stormwater collection from 200 to 400 to 600 acres of drainage area, then those actual costs are driven down by this reduction in fees, which is applied against their bill. And in fact, by the time they get to about 600 acre feet of stormwater collection, they're not going to be paying for their water. And they're putting water back in the ground, which can then be delivered to another ratepayer, helping to support the revenue stream of the agency. So we got together with the Resource Conservation District of Santa Cruz County and put a proposal forward to the Board of Directors of Pajaro Valley Water in January. And this was studied. They put it out to their committees, the technical committee, their project committee, to look at whether or not this was something they would like to try, and it was approved. It was approved at a board meeting in March, and I can provide more information about the particulars of the program, but here's a quick overview of how it's going to work. It's a 5-year pilot. It will sunset automatically at 5 years, so nobody's locked in at this point to doing it. Our goal in this is to see if we can make it work. What do the numbers look like? How many people want to participate? And what kind of benefit can we demonstrate? There's a third-party certifier, which will be us and the RCD, and we will help to identify sites, working with landowners, customers, the city of Watsonville, which is the single largest pumper in the area, anyone who wants to participate, help to find the right sites based on a variety of analyses I didn't have a chance to show you, but I'll talk about a little bit tomorrow. Raise the capital costs to build these projects, get engineering designs. The RCD is terrific with the permitting. We're working with them on the permits. We work with the landowner to develop a plan for the measurements and sampling and monitoring that are required in order to certify the net benefit. Then the third-party certifier prepares the annual report, delivers it to the ratepayer and to the agency, and they provide a credit according to a formula, which for the pilot program will be 50% of the augmentation fee for that part of the basin, less the incidental infiltration that would have occurred anyway. So the agency then reduces their water costs for the previous year. The goal is to put 8 to 10 of these projects online in the next 5 years. We have one that I showed you already that's currently operating, and there are 3 more that are in the engineering design phase right now, and we hope to start bringing them online and then solicit additional projects as well. So it's clear that something exactly like this may not fit the Central Valley, not exactly like this. But I think perhaps in concept, as the GSAs are forming and they're developing their funding streams, which they have to do in order to operate. If we could build in incentive and rebate programs along with the fee programs, it may make them more palatable and more functional overall within some of these basins. Thanks.
Great. So if all the panelists want to come up to the front now, we can. I'm going to ask. I've got a couple of questions I want to just ask of the whole panel, since these were all sort of separate introductions to the idea here. You all have introduced different methods of recharge, whether it's on sort of natural restored floodplains, on farmland, or in a managed aquifer or in a managed basin. I just wanted to point out for everyone, the diversity of situations in California really require this whole variety of these different methods. But the question I wanted to bring to all of you is, what % of current groundwater demand could be realistically offset? And I know it varies around the state, and some of you gave some of the numbers on this. But as we think about the sort of the crisis the state's in terms of overdrafting, how realistic is this? Is there enough water, and are there enough places to put it to actually see a significant offset?
When we pitched the net metering program to the board of directors for PVWMA, we pitched it as a 10% solution, with the idea that we would try to address 10% of their calculated deficit based on a basin management plan and a groundwater model. Part of it was keeping the expectations low enough that we could succeed, frankly. It may be there's enough interest and it works well enough that we could do better than that. But in this area in particular, I think that's what we might be shooting for. I'll make one other comment on a statewide basis. I add up the numbers from the DWR's water plan update every year. And, although nominally that number of the statewide deficit for groundwater is 1.5 million acre feet or 2 million acre feet, in fact, if you go to the last report from 2013, the deficit between supply and demand that they label to groundwater is about 12 million acre feet per year during a normal year, and it's 15 million acre feet during a dry year, and it's a 5 million acre foot deficit during a wet year, is what DWR says right now. Now, they may not use the O word to describe that, but it sounds like overdraft to me. So I think the problem is a lot bigger than it's stated in many cases. We're going to find out more as SGMA is developed and we actually get budgets for these basins. But I think this is a huge problem, and we need to start taking all of these approaches where they're appropriate, different approaches for different parts of the state.
And wetlands.
Yeah, I don't know.
Floodplains. Yeah.
Well, from wetlands alone will not do it. But it's just one of the tricks in the bag of tricks that one can use. In terms of how much, let's say the overdraft is 1 to 2 million acre feet. How much of that could be erased by these kinds of measures? Well, maybe most of it. But I don't think anyone's arguing that all of the overdraft can be taken up by just recharging. But I think as the future goes on, the kinds of climate shift problems that Irfan was referring to get worse and worse. So it's going to be harder and harder to store surface water. It's already happening. So the more you can store in groundwater, the better off you will be, is basically the mantra.
Helen, you care to comment any further? You gave some of the numbers earlier.
Yeah, I mean, I was not aware of the newest report. I would say with the amount of water that we have in California, we all can manage, but I see actually the legal and the policy hurdles as the biggest impediment to actually managing water in California efficiently and sustainably. So I think we are definitely not running water. I've seen a few newspaper articles on that last year that big headlines, is California running out of water in 100 years? I don't think so, but we definitely have to change a couple policies and maybe even laws to make it happen.
Irfan, care to comment?
Just a quick comment. I just look at, instead of numbers, I look at the percentage. So we all know that about the use of groundwater in California is about like 30% normal to 60% in dry years. So if we look at also just American River and look, we just need like 10% of total natural flow during wet season to capture that much water for groundwater. That's a huge increase, like preventing the overdraft, at least in American River.
Another question in terms, this is the accounting discussion. In terms of how you all have measured the amount of recharge and the benefit of that, as Sigma GSA start to grapple with measuring the benefit or the credit of this, where are we at with the ability to feasibly measure recharge through these different methodologies? Is there an affordable, effective methodology at this point?
Well, in basins where the groundwater is way below the rivers and you can monitor the water table, it's relatively simple. In basins where the water table is high enough to be connected to the rivers and where some of the recharge may go out to the rivers, it's a little more complex, but it's hydrogeology 101, basically. It's possible that in about 10 years we will have the equivalent of the GRACE satellite method that will be operational down to the 50-kilometer time scale. Currently, GRACE is not that useful for this kind of thing because the footprint's too big. But in about 10 years, it's possible we'll be down to that 50-kilometer scale where satellite information will give us good information on groundwater storage changes.
And how about at the site-specific level, Helen or Andy?
For our projects, we're using two methods: mass balance, what flows in. We've done calculations since much of the infiltration occurs during the wet season when evaporation is relatively slow, and the time scale of infiltration is so quick in comparison. ET tends to be at the percent level of the total mass balance. So really it's just inflows and outflows, and then you take the difference. The other approach we're using is using heat as a tracer. We have some probes that we build that we put in the ground and monitor the transfer of heat from the surface into the ground, and that can be turned into an infiltration rate pretty accurately. And we find those numbers match pretty well. If you distribute the probes around the field, you get pretty good numbers, provided you saturate the soil. When the soil is going wet and dry, it makes it a harder measurement. And we think between those two, it's good enough. If we're within a few percent or even a few tens of percent, when we consider the goal of 1,000 acre-feet, if we only get 800 or we get 1,100, I'm good with that. I think it's close enough for us to get going. And I think the methods will continue to improve, particularly if there's demand. If there's interest and the numbers really matter, then we'll figure out better ways to make those measurements.
Yeah, I can maybe add to that. One of my colleagues, Wes Wallander, who retired last summer, he always emphasized measure your control volume, and I think many farmers are doing that anyways. In particular, when they have pressurized systems, you often have a meter on the system. For those that are diverting surface water, I think there is a fairly recent bill or a regulation put in place that is asking farmers to report how much water they are diverting. And so it would be good to get that data into some sort of database and use it also, for the purposes of winter recharge.
Final question before we open it up to the panel. Andy introduced the idea of incentives and this idea of net metering. For the rest of the state and other locations where you don't have a pricing system already in place for pumping, what are the preconditions do you see in terms of being able to see widespread adoption, either of people considering floodplains or farmland for recharge? What's it going to take? What are some of the incentives? Or is it what aspect of GSA or Sigma implementation is going to be needed?
I can say a quick word. I mean, I've worked with a couple of growers now on these recharge projects on farm, and at the beginning when we started, there was a lot of opposition, and that had changed really quickly once the drought became more severe. And so in the past year, actually, most farmers have said, I just want to do it for the purpose of recharging the groundwater so I have some water next year. And which is, really refreshing to see. And as incentive systems, actually, Paul Hendricks should probably stand up and say a couple words about that. So I'm working with Tulare Irrigation District, and they have offered their landowners $150 per acre, I think, last year, if they sign up for ag recharge in the winter. And then they offered even a greater incentive if landowners actually took water onto their field for recharge. And that was really a system that was just, put in place by the irrigation district themselves, and farmers definitely responded to that. And so it was sort of a self-organization that was very interesting to see that happened and didn't really take much effort to put in place.
And Paul will be up in the last session later today.
Yeah.
So. Good. Okay, we'll open it up to folks with questions.
Okay, that's good.
Yeah.
I just have a question. So, when I think about soil, about groundwater recharge, I think it's a function. Maybe it's a function where you have we have different climate zones where we have different average rainfall. But the biggest way to recharge is at the farm level, and it's from rainfall. And so it really goes to soil structure and percolation rates. And that goes to organic matter and whether or not the soil structure, if you're going to have recharge and percolation, you have to have a full root zones. So I think one of the issues, maybe it's a little bit counterintuitive because everybody's thinking about saving water, but in some basins where you have, say, 12 inches of rain during the wintertime, maybe we should be doing sprinkler irrigation versus drip to have a full root zone and really focus on organic matter and water holding capacity, but also just percolation, because what's happening is when we have 18 inches of rain in the Sacramento Valley, especially with drip, 13, 14 inches just runs off right now. And given the constraints we have to survive for the environment in the Delta, a lot of it has to stay in the Delta anyhow, and we can't get it south. But if we actually could bring that in, wherever we have higher rainfall, we should talk about the agronomy and soil structure, because it's great to flood, but Mother Nature floods, and Mother Nature broads it, and that's a broad distribution. So I think what's missing this whole thing is this counterintuitive one. Maybe you really want to have more water on the soil to keep the soil structure for long-term fertility, and that's the best way to get access for a broader area.
Just want to focus on any questions you guys have for the panelists, and then I will open it up also for other additional ideas, especially from our international folks here. Any question just to clarify any of these presentations? David?
Yeah, it's a conundrum here within California. Your land regulatory program says they don't want salts and nitrogen going below the root zone, yet Sigma says we're going to have to recharge like gangbusters to get the aquifer in sustainability. The two are opposed, so who's going to win and how is that going to happen, especially seeing as how right now recharge is not a beneficial use?
That's a great point, but they're not in opposition. And maybe for reasons that are not so obvious yet. For one thing, we think that we've shown in the groundwater community that the groundwater quality in the Central Valley is on a long downhill decline and is not sustainable on a decadal to century time scale. And the only thing that will reverse that is introducing a substantial amount of relatively clean recharge. And we can see it. We can see halos of relatively nitrate-free water around spreading basins like Leaky Acres, adjacent to losing streams. So we know that the encouragement of relatively nitrate and salt-free recharge is beneficial. And on Thursday, I will have a talk that argues the only way to make the salt balance of these basins sustainable will be to fill them up a lot more than they are now. Otherwise, we're creating a mono-basin, salton sea, Great Salt Lake on the long term. So it's all pointing towards, Yes, possibly causing some water quality problems and needing to deal with, as Helen suggested, with the legal and regulatory framework differently. But the first step is sort of getting a handle around what the consequences of all these things are. And in the long view, if we can see, what could improve the water quality while also maximizing the water storage, then that's probably the direction we should be going.
But as a farmer right now, I'm being told I can't do the one.
Helen, do you want to comment on that?
Yeah, so beneficial use definitely is, groundwater recharge is not a beneficial use, but the water board is not necessarily interested in just putting water into the ground for the purpose of putting it into the ground. As long as you're putting it into the ground so you can take it out later on for irrigation, I think they're very happy with that concept. And so you can actually apply for a temporary groundwater recharge permit, putting irrigation as a beneficial use on the permit. And we haven't quite figured out how to make all the numbers work out in the end. So meaning if you put 100 acre feet into the ground, how do you know that you get that back or that you are going to be the first one using it? So those are ongoing discussion topics, but I think everyone is definitely aware of that problem, and it's definitely, the water board is very much interested in trying to figure out how to solve it. And I also wanted to maybe comment on the question of the conundrum. The soil map that I showed that shows suitable soils for ag recharge, that one has roughly identified 3.5 million acres in the Central Valley would be suitable to do recharge on. However, if everyone just puts in 6 inches or 12 inches of recharge water on their field, then yes, we only wash down the nitrates and the salts. But if we would put on maybe 6 feet or 8 feet or 10 feet and don't do that on the 3.5 million acres, but maybe only on 100,000, then you're creating a scenario where you can actually cause dilution of the nitrates and the salts in the groundwater underneath it. So, and that's, I think, what we should be aiming for. We're not trying to say everyone, or let's say half the farmers' population in the Central Valley should do ag recharge. I think it will come down that we have to figure out which cropping systems can actually deal with it, can tolerate it. And ideally, that's why we have started looking at alfalfa, which is not a fertilizer receiving crop. So you actually have maybe some chances of getting some clean ag recharge happening. Yeah.
Yeah.
Should there or are there any concerns about loss of ecosystem services or water deprivation from downstream users because we're capturing stuff that would otherwise be runoff or taking out a diversion to put on agricultural land?
Yeah, so we've thought about this, and there's a couple of answers. It's a legitimate concern. The first answer is that groundwater recharge and infiltration in general is a hydrologic system service. It is intrinsically beneficial, and it needs to be valued as such. So that, I think, is a process. I think we're going to need to get there, recognizing that the mere act of putting water into the ground, particularly in developed areas where because of changes in land use, less infiltration is occurring than used to occur under natural conditions, that's a step towards hydrologic system service restoration, and it is intrinsically beneficial. That's the first point. The second point is, in the case of the stormwater collection, it occurs on hill slopes, not blue-line streams, so there is no water right conflict. The third issue is that it focuses on the collection of the tips of the flood flows during the time when the river and streams are at flood. There is no environmental negative effect. It's very important in this system when we compare what we're proposing to do in Pajaro Valley to the total runoff for the basin. It's hundreds of thousands of acre feet. We're trying to get 1,000. So again, you're at the percent level. And I think at that level, the negative impacts are trivial. Obviously, if you spread this out all across the landscape, like Helen's describing, and you got all of it, well, yeah, that would be problematic. If you got all of it in the spring, when the flows in the streams are down to 10, 5, 2 CFS. Yeah, that would be a big problem. But when you're taking the tips off the floods when the rivers are at flood and you're collecting a small fraction of the hill slope water, it's fine. I don't think that's a problem. We have to manage this very carefully. We have to do it right. We have to permit the projects and do them carefully. But I think if we can show that there's no negative effect, then it will become people will become accustomed to it. And I think then we'll be able to make more progress.
And just to comment on the benefits of recharge, the biggest ecological transformation in California was the conversion of 20% of the valley that used to be wetlands and riparian ecosystems into a system that's more like 2% wetlands. And that was because of the lowering of the water table. So anything that elevates the water table back up so there's a little bit more base flow and maybe some wetlands here and there can be construed as ecologically beneficial and providing a natural ongoing outlet for salt.
I just want to make a broader comment about this, beneficial uses of carbon recharge. I do agree with Andy that there is intrinsic benefits to it, but there's also been lots of evidence that shows that groundwater recharge has a lot of co-benefits with improving groundwater quality, in reducing seawater intrusion, increasing wetland habitat, reducing greenhouse gas emissions, flood protection. So the list goes on, and so it's something that can be used as a tool to achieve multiple benefits.
Just want to encourage anybody internationally, if you have similar perspectives. You got one in the back there.
This is Vinay from ICS. I'd like to share one that recharge PS in Japan. It's in Kumamoto, Japan. They don't have surface protections. The one is also on the groundwater. So they have an alliance with like Sony company and farmers. So farmers allow their rice to be recharged, and Sony company pays some of the amount because they also use the groundwater. That's the first thing. And second is I think maybe we apply to here in California is like the rice they produce, farmers produce, they put tag on it, like something like it's a recharged rice. So they get a little bit higher price in the local market. I think that's the saving basically.
Anybody else?
So in India, they have this traditional water harvesting technology, which has been used for millennia, but was eradicated when the British came in and built all these canals. And I would find it really interesting that they use such a low-cost approach to recharge and facilitate decentralized recharge of monsoon water. So they build these things called check dams and cuts, which are basically stone structures and field runs that surround the farmers' property. And so it not only improves the soil quality because it reduces erosion, but it also facilitates greater percolation of monsoon water. And during my time in India, I saw a lot of benefits that farmers gained from doing this because they were able to grow 2 or 3 crops versus 1 because they had higher groundwater levels. And when we think about trying to respond very quickly, like for this past El Nino year, we had a lot of water, but we didn't really have the flexibility to react to it quickly. And so I really like this concept of this voluntary groundwater recharge program that Andy's leading up, and we could just create systems that were more flexible so that people can respond to availability of water. That would be great.
Any other comments or questions? Yeah.
I have a question. I'm Tim Bailey from Tulare County Environmental Planner. And there's an alternative scenario that I see. Right now, PPIC is using figures from 2015 and 2016, I think that are accurate. 10% are reduced, 40% ag use, 50% ag use for water across the state. An alternative scenario that I see, we lose agriculture in the Central Valley due to hydrological failures or market changes, et cetera, is, I know the visual numbers, the population of 15 million by the year 2050. Currently, we're about 38 million and change across the state. Most of that basically a parallel from Texas on south, the majority below the Grapevine. We're talking about 7 Fresno-sized cities I've seen in the literature needing to be placed in the Central Valley to accommodate coming population growth. We're we're talking a lot of studies documenting climate change, ongoing climate change, reduced snowpack, reduced recharge across the region. Do you guys factor that in? Do you have a scenario as to what the valley looks like and what, particularly what groundwater recharge looks like in that sort of scenario? Right now we're talking about, we've got ag uses, we've got groundwater overdraft perhaps due to agricultural activities, etc. What happens if we lose our agriculture and just become a gray kind of non-scale across the valley, like city after conservation? I know we'll lose recharge because the water will be able to percolate in unless we go with permeable paving and things of that nature. I know that there may be a reduction in groundwater overdraft because urban areas tend to not use too much groundwater as we actually in some cases. But if we've got tens of millions more people in this valley now because it's no longer an agricultural zone because we've lost our rivers and ag lands, what does that look like as far as hydrology and recharge? It's kind of broad.
Somebody want to tackle that one?
Yeah.
And we have a session later on in terms of the future of the valley.
I think it's a few too many hypotheticals for me to do a good job on, but let me just say it's not a foregone conclusion that recharge will decrease except in areas not fed by the mountains. In the Central Valley, it's recharge from rainfall infiltration will decrease because of higher temperatures, even in winter when the ET rates are low. But if we have higher river flows in winter, and there's a lot of recharge from the rivers, and in particular designed flood basins for the water to go and sit for a long, long, long time, it's possible that winter recharge in the Central Valley under climate change, yes, would increase under that scenario. But that's due to the geography of the Central Valley and the way the rivers and groundwater basins are. The rest of it, I guess I don't envision agriculture going away completely, but I'm not a land management planner.
Okay. Yeah, Jay?
This is really great. A couple of thoughts. It sort of seems to me that the hardest part, two hard parts of this are likely to be, one is there's not a lot of surface water available to flood relative to the whole lot of demand. I mean, it's a good thing, but it's not going to be a silver bullet for sure. And it varies, as folks have noted, between the northern part of the valley, where we have plenty of groundwater pretty much, versus the southern part of the valley, where we have lots of empty space. So there's some really big strategic issues there. The other aspect, and I think Andy's work touches on it nicely, is the need for a financial model for this to work. And why would farmers do this, and how would you pay them to do that, and do the right accounting on that water to keep it going. I'm intrigued by your idea, Helen, of addressing the water quality aspects of some of this to have some farm plots specialized in recharge to some degree, where they have suitable soils and suitable empty groundwater space. To the degree that if you were organized enough and had a right financial model, you could maybe pay farmers to forego some agriculture that would use higher amounts of nitrogen, say, to using lower amounts of nitrogen. Essentially, their farm is now partially recharge based and partially farmed. And how that would be optimized might be it. But the financial models, I think, are key. And the net metering that Andy suggests is an interesting model, but I think also we should be looking at some kind of water market kind of mechanism for other parts of the valley.
Let me just add one piece of that just for the panelists. There's also a lot of prediction that there will be reduction in cropped land as a result of pumping restrictions, even if we do allow the recharge. So how critical is it to have recharge on active farmland versus on the fallowed land, which could be basins, it could be wetlands, it could be a variety of other uses?
Yeah, we've also done some spatial analysis to try to find the sites that are optimal, and that's part of our pilot program, is to really cherry pick the best locations. And I think the data sets like out of the Davis group, Toby Eugene's work, and our study, which is somewhat different, but it uses complementary analyses, is a good approach for screening. You still have to look at the particulars. Soils are highly heterogeneous. That site I showed, it's a good recharge site in part because it's a paleo river channel with very coarse materials, and you step 50 feet to the east or west, and it's a different soil. There are other technologies, though. Dry wells might be used in some places where you need to get below the soil. The other thing we're working on, or another piece we're working on, is improvements to water quality with the use of permeable reactive barriers along with infiltration. And our results are preliminary so far, but they're promising. We've seen up to 40% nitrate load reduction with simple wood chips, 40 centimeters of wood chips, even with infiltration rates as high as 10 feet a day or more. So I just think we're at the beginning of this. I think when we know what our goals are, we can meet multiple objectives. We can find the best places where we can meet 2, 3, or 4 objectives at once, and it won't be everywhere. I think that's the key. To me, that's a common thread of all of these, is that if we can find the right places for the right project, then it won't be as expensive or as difficult. I will acknowledge it's hard to scale that up, and there may be a limit. But I think we should start with the places where this is the easiest to do and we can get the most improvement to supply and quality. And I think there's a lot of opportunities out there right now where we could do those tests and get the hard numbers to really tell us how this is going to work.
I think we're going to have to wrap it up. Final comment?
Well, I was just going to say, I do think the financial model is really critical, because I think that we'll reach a peak in recharge interest, but when people discover that their recharge, which is local, regionally benefits a lot of people besides they who are doing the recharge, their incentives to do the recharge will go down. And that's a fact. The groundwater recharge is local. The benefits are regional. So there has to be some kind of financial or other incentive for someone, for hundreds of people or thousands, to initiate those recharge projects.
Helen?
Yeah, I wanted to maybe throw out a complete crazy idea, but I don't understand why we always have to manage within our community. So why do all the water managers have to come up with a solution for solving the water problem? California has a farm output of $54 billion a year. Why can't we translate some of that cost onto the consumer? Everyone likes to eat peaches and blueberries from California. Why not take a cent off of that price and put it towards water infrastructure and water management? I personally don't even know the price of blueberries and peaches right now, but I don't think I would care if it's 1 cent more expensive per pound than less. So my thought.
Irfan, any last closing comment?
I just want to mention something else again about the surface water, because I'm looking from another perspective. I look from surface water and see how recharge can help the management of surface water. For example, imagine we have the Folsom reservoirs, and with that more advanced reservoir operation and reoperating the Folsom, we can just capture the peaks. So, like almost all the reservoirs in California, they are operating based on the rule curves. When you're going above the rule curve, you have to release the water anyway, with no purpose but protecting the flood in reservoir. So this much water, if you have a more advanced operation of the reservoirs, you can pre-release this much water to groundwater and just to groundwater budget, and then keep it there instead of wasting the water.
Well, thanks to our panelists. We're going to transition to the next one.